In the first 6 months of 1965, Centaur's single-burn research and development program was near completion. Previous R&D flights had successfully demonstrated all of Centaur's major flight systems. Only 2 test flights remained before Centaur would become operational, ready to launch the Surveyor spacecraft to the moon. March 2nd, flight day for the 5th experimental Atlas Centaur AC-5. Its mission objectives: to verify flight results to date and demonstrate 4 new systems, including the release mechanism for payload separation. This was to be the first time a dynamic model of Surveyor would separate from Centaur and begin its flight to a hypothetical point in space, a paper moon target. Countdown proceeded smoothly to T-minus 5 minutes. Then the count held 40 minutes to demonstrate Atlas Centaur's ability to stand fully fueled for a pre-planned length of time. No system degradation due to cryogenic effects was noted during the hold. After an almost perfect countdown, AC-5 launched on time at 8:25:04 Eastern Standard Time. At the time of the flight, the Atlas launch vehicle had set a record of 28 consecutive successful flights without a mishap. Analysis of motion picture films did not reveal abnormalities in any systems until flameout of the thrust chambers. All that was known was that 2 seconds after liftoff, Atlas booster engine shut down and the vehicle fell back into the launcher, where explosion and fire destroyed it. Test data showed that all engine sequencing and thrust buildup was normal until loss of fuel at the V1 and V2 fuel pump inlets. Examination of actual engine system hardware indicated that thrust loss was caused by fuel starvation. The most probable cause was closing of the fuel pre-valve, which blocked fuel flow to the booster engines. The pre-valve is located at the outlet of the RP-1 tank and is used during pre-flight ground operations to keep fuel out of the engines and to maintain tank pressure during maintenance or storage. It also serves as an emergency fuel shutoff during engine testing. Detailed analysis of recovered hardware revealed that the pre-valve was closed at the time of the pad explosion, indicating that it had not locked fully open before flight. A pneumatic actuator operates the pre-valve. It is designed to lock the pre-valve open by means of an internal ball detent mechanical lock. Examination of the actuator mechanism showed no evidence of mechanical flaws to prevent it from stroking fully open and locking. However, bench tests revealed that several complications could be induced which would permit the pre-valve to partially open to a semi-locked position. Even though the valve is not locked fully open, a full open indication could be received at the control console. Flow tests at the Point Loma test site showed that fuel flowing through the semi-locked valve initiates enough force to close the butterfly flap, shutting off flow to the engines. Continuing investigation in the analysis lab uncovered 5 possible system faults or failures which were capable of leaving the valve in the semi-locked condition. However, review of flight histories of more than 200 Atlas flights showed no reports of pre-valve failures. Immediate corrective action involved installation of a mechanical locking device on both the booster and sustainer fuel pre-valves. Range crews will install the lock just before flight to prevent the pre-valves from leaving the open position. While failure analysis was underway at Convair, program officials were estimating the extent of pad damage to begin plans for rebuilding the burned-out pad. Convair assigned aerospace construction expert Chet Dunn to the task. Dunn directed engineering of the nationwide network of Atlas ICBM sites, a project called one of the biggest construction jobs in history.
The launch stand and umbilical towers were badly burned, but pad damage proved less severe than it had first appeared. The launcher, wiring, ducting, and the transfer room suffered the most extensive damage. The task of repair involved cleaning and replacement of burned-out parts, followed by validation of systems. The biggest problem was to get lots of parts and cables in a hurry. Fortunately, many of the major items, for example the launcher, were available from the disaster pool maintained by the Air Force. The steel beams in the umbilical and launch towers did not sustain structural damage and only needed cleaning and painting. Most of the rehabilitation task had been completed by the end of June. At that time, validation of ground support equipment and systems was underway. The complex will be ready for launch operations by late summer of 1965. Shortly after the 36A incident, NASA officials decided to shift the next scheduled launch, AC-6, to Complex 36B, which is adjacent to Complex 36A. At the time of AC-5, 36B was inactive. However, it was structurally complete, with most of the wiring and ground support equipment already installed. Some modifications were necessary to bring the facility up to an AC-6 configuration. For example, the horizontal swing boom assemblies originally developed by NASA for the Saturn program were installed at Complex 36B. Evaluation tests of these booms were conducted here at our Point Loma test site. Test articles consisted of upper and lower boom arms, arranged so that they attach to a dummy Centaur at the same level. At ETR, the booms are located one above the other. Tests established that the umbilicals eject and retract correctly, and that the booms start correctly, rotate clear of the vehicle, and stop within specified limits. Lines which the booms support are part of the air conditioning, electrical, pneumatic, and the propellant loading and vent systems. The unexpected workload at 36B, over and above the refurbishment of 36A, imposed some problems. But the complex was ready in time to support the next scheduled launch. A great deal of the preparation for the next flight test has been under the direction of F.X. Marshall, manager of program coordination for Convair.
Because the aborted flight of AC-5 caused a no-test situation for the Centaur second stage, the mission objectives for AC-5 will have to be satisfied during the flight of AC-6. Some of the more important features of the AC-6 flight will be the launch on time capability, the flight integrity of the new configuration, the performance of the MA-5 booster engines, the guidance system flight control command system, the surveyor flight environment, the Centaur tank retro maneuver, and finally, the accuracy of the final flight trajectory. The configuration of the Centaur stage for this flight includes some noteworthy improvements. For example, the new D-series tank is lightweight. Its skin sections have been reduced from 16 thousandths to 14 thousandths of an inch gauge steel. The intermediate bulkhead has moved 4 inches aft of its former location, optimizing the size of the tanks to provide for more optimized propellant burnout condition. This in turn has resulted in added vehicle payload capability. The interstage adapter has also been redesigned using lighter metals and some chem milling, reducing its weight by approximately 550 pounds. Forward and after bulkheads and the thrust barrel have also been redesigned using lighter gauge steel and chem milled parts. The weight saved on the D-series tank amounts to about 155 pounds. The changes called for major ground system testing. Of particular interest are 2 highly critical stress areas on the tank. The Station 219 ring, which is the interface between the Centaur and the Surveyor nose bearing, and the Station 412 ring, which is the interface between the Centaur and the interstage adapter.
At K-Tower, a special fixture attached at the nose-fairing barrel applied loads at design limit and ultimate capacity levels to simulate maximum loading expected during flight. Closed-circuit television served as a versatile instrumentation tool, providing engineers a means of constant and immediate surveillance. Loads up to 60,000 pounds were applied simultaneously in increments of from 20 to 125% of ultimate design limits. Test results showed that the D-series tank can withstand loads well above its ultimate design limits without detrimental effects. At M Tower, other design evaluation tests were underway to demonstrate that the AC-6 aft bulkhead design was sufficient to support operational loads. Hydraulic rams attached to the bulkhead applied loads simulating flight and static engine conditions. The loads are equivalent to the severe flight stresses Centaur encounters during periods of maximum aerodynamic loading in flight. Test results indicated the structural adequacy of the bulkhead and ability of the lighter thrust barrel to distribute concentrated engine loads into the aft bulkhead. Successful completion of the test removed another constraint from the AC-6 flight. In changing to a D-series operational tank, other major systems were affected, requiring redesign and testing. The longer hydrogen tank meant extending the insulation panels an additional 4 inches for adequate insulation. Evaluation tests of panel sections verified structural soundness of the new design. Concurrent with panel development, engineers designed a new shaped charge system for use in separating the panels from the Centaur tank. The more reliable system eliminates complex components which were difficult to install and required critical adjustments. The shaped charge, now on the outside face of the panels, is easier to install and to get to for maintenance. Its performance has improved, so it can now operate in an air atmosphere of temperatures ranging from minus 423 degrees Fahrenheit to plus 250 degrees Fahrenheit. Tests demonstrated the insulation panel separation from the liquid hydrogen-filled Centaur tank. All pyrotechnics fired, and the insulation panels unlatched freely. The new shaped charge system was also incorporated in the redesigned changes for the AC-6 nose fairing. Both the new shaped charge system and the explosive separation latches are designed to generate minimum fragmentation when activated. Past tests with R&D fairings have shown that an adverse environment can exist at the moment of separation due to debris floating free inside the fairing. A new pyrotechnic stopper valve replaces the bottle pin and stopper mechanism, which in earlier tests had dislodged pieces of hardware that could impact the spacecraft. The deflector bulkhead rails were also rearranged to more safely clear the surveyor mast and S-band beacon during separation. Other changes to the fairing include modified air conditioning ducts to provide increased clearance between duct and electronic packages, installation of television target lights for aligning surveyors' cameras for operational missions, and structural modification of the base of the fairing to assure proper fit to the new tank's T-shaped 219 attach ring. At the Lewis Research Center's Space Power Chamber, the AC-6 fairing jettison system demonstrated its ability to operate satisfactorily at simulated flight altitudes. Jettisoning did not produce any undesirable effects on the simulated payload or on the nose fairing assembly, thereby lifting a restraint on AC-6. Combining the lightweight AC-6 hardware with the new linear shaped charge system made it necessary to rerun evaluation tests on the Centaur Atlas separation system. 7 runs under simulated atmospheric flight conditions in the Lewis Space Chamber demonstrated smooth separation of Centaur from the Atlas interstage adapter. These tests were also considered a restraint on the AC-6 flight. The new lightweight interstage adapter had to pass a series of proof tests at General Dynamics Fort Worth before it became flight-worthy for AC-6. Though lighter, its chem-milled stiffener design is extremely rugged. Structural tests subjected the adapter to loads 200% greater than its design limits. The adapter withstood the forces without evidence of permanent set or visual damage. New systems to be demonstrated aboard AC-6 include an electromechanical timer, which replaces an electronic digital clock for signaling in-flight sequence events during the one-burn mission, a refined, lightweight range safety destructor mechanism, and an advanced propellant utilization system which produces a balanced flow of the 2 propellants so they are used at the same rate, leaving no residual propellants in either tank. The AC-6 flight test will be a dress rehearsal for the operational flight of AC-7, scheduled to soft land a Surveyor spacecraft on the Moon in the fall of this year. To achieve payload injection, AC-6 will begin a rapid pitchover to reach the velocity for the flight mission. Flying this low, flatter trajectory will impose greater loads on the space vehicle due to aerodynamic heating and stresses developed in the denser regions of the atmosphere. The flight will test Centaur's ability to accurately inject a dynamic model of Surveyor into a simulated lunar transfer trajectory. Centaur's payload separation system will operate for the first time, releasing Surveyor on a course in the direction of an imaginary or paper moon. Since the launch occurs at a time selected so the Earth and Moon are not aligned with each other, no actual lunar intercept will occur. Instead, the dynamic model will be in a highly elliptical Earth orbit. Shortly after the Surveyor model separates, Centaur will perform an in-flight turnaround and retro maneuver. Attitude rockets will reorient the vehicle to the flight path. Residual propellants will discharge unignited through the main engines. The expelling liquids generate reverse thrust, which slows Centaur down to increase the distance between it and the payload. On operational flights, this maneuver will prevent Surveyor's guidance from locking on the Centaur tank as a navigational reference. In tests at Convair, engineers evaluated the performance of the separation system and new latch hardware. The setup consisted of a Surveyor dummy mass model and a Centaur adapter assembly which houses the spring separation mechanism. An air-bearing, air-spring suspension system simulated, as nearly as possible, the weightless, friction-free environment of space. The spacecraft moved freely in 3 axes in response to separation forces. Instruments on the floating spacecraft detected movement and attitude change. The Surveyor dynamic model, which will fly on AC-6, approximates the operational spacecraft in moment of inertia, center of gravity location, and natural bending frequencies. The 2,100-pound model is inert except for telemetry and tracking equipment. No functional propulsion, attitude control, or other Surveyor mechanisms are installed. In April, Atlas 151D and Centaur 6C completed factory acceptance and moved into the interim combined systems test dock for composite systems checkout. In this facility, Atlas Centaur 6 and the dynamic model were electrically mated. The combined space vehicle flew a simulated lunar mission to demonstrate overall systems compatibility. The composite test duplicated actual pre-launch and flight conditions as nearly as possible. After the demonstration, Atlas Centaur was airlifted to ETR. In May, range crews erected AC-6 into the stand at 36B to begin pre-flight checkouts. In late March, Atlas 174D, booster for AC-7, passed factory acceptance tests and moved into NASA's new Combined Systems Test Facility, or CSTF, in San Diego. The CSTF facility, located adjacent to Convair's main plant, accommodates all stages of a space vehicle and its spacecraft payload for ground testing. Here, Atlas, Centaur, and Surveyor are combined as a functioning system capable of flying simulated lunar missions. The purpose of Combined Systems Test is to establish the overall flight readiness of the Atlas Centaur Surveyor before shipment to the Eastern Test Range for launch operations. Centaur 7C and Atlas 151D are the actual flight articles to be used for AC-7. The T-21 Surveyor spacecraft, however, is an engineering prototype of the lunar spacecraft SC-1. At the time of the tests, SC-1 was completing final work at Hughes Aircraft Company. For the composite simulated flight demonstration, technicians encapsulated the spacecraft and mated it atop the Centaur and interstage adapter. From the CSTF control room, arranged to simulate the complex 36 blockhouse, launch crews conducted a complete simulated flight from launch through Centaur retro maneuver, including operation of the spacecraft. The CSTF demonstration enabled Convair, Hughes, NASA, and JPL personnel to detect and rectify possible problem areas before shipment of the flight vehicles to ETR. Test results indicated several areas of non-compatibility between vehicle and spacecraft, which required GSE, airborne, or spacecraft changes. The true value of the CSTF lies in the fact that these discrepancies were detected early, while the flight vehicles were still near their manufacturing facilities. CSTF tests also reduce the amount of testing usually necessary at ETR, thereby shortening on-pad pre-flight operations. This means that upon arrival at ETR, Centaur Surveyor will be ready to launch sooner, better able to meet launch-on-time requirements. AC-7 is scheduled to leave San Diego in July for ETR, where it will be erected with SC-1 at Complex 36A. With the bulk of Centaur's research and development complete, attention is now focused on AC-8 and development of the two-burn mission capability. Early in 1965, the configuration for the two-burn mission was finalized. On the AC-4 flight, the engines did not achieve the planned second burn experiment because of propellant starvation at the engine pump inlets. New design changes for AC-8 are planned to assure propellant supply to the pumps. 1/10 scale Centaur propellant flow tests indicated that certain hardware changes and additions would greatly reduce propellant movement in the tank at main engine cutoff. The scale model tests were effective in evaluating baffles, diffusers, and volute bleed recirculation methods. Manufacturing began in May on full-scale hardware. A new hydrogen vent system has also been devised. It will replace the wide duct vent used on AC-4. The new system, still in the mock-up development stage, consists of a torus ring with vent ports located 180 degrees apart. In space, the ports will vent simultaneously. The opposite thrusts generated will nullify each other. When combined with the other hardware fixes, the vent system will prevent liquids from venting and affecting the attitude of Centaur in free-floating space. The AC-8 Centaur vehicle is about 85% complete in final assembly. It's scheduled for flight in 1966. Other Centaur vehicles were in various stages of fabrication. The vehicle for AC-9 completed tank fabrication and moved to the X-ray inspection area before beginning final assembly. AC-10 Centaur has been advanced in its production schedule to serve as backup for AC-7. In June, crews ran continuity checks of all wiring and electrical systems. The Centaur vehicle is now 95% complete. AC-11 was just beginning final assembly. Main activity involves installing the aft radiation shields. AC-12's tank received its intermediate bulkhead, while forward bulkhead buildup has just begun for AC-13.
We were all disappointed when the Atlas booster failed on AC-5, ending its string of 28 consecutive successes. But we were not discouraged. We pursued with vigor and determination the task of rebuilding our launch capability and preparing for full support of the Surveyor mission schedule. The 6th Atlas Centaur experimental flight test is an operational prototype for direct descent missions. Its successful completion will make the Centaur fully operational as a launch vehicle for the National Space Program. Already, the National Aeronautics and Space Administration is planning the use of Centaur with the Saturn 1B booster as a launch vehicle for the Voyager mission. We will work with other mission planners to assure that they have accurate and complete information on the operational capability of the Centaur high-energy upper stage for use with the Saturn, Titan, and Atlas boosters.